Yeah, good morning, everyone. This is my second note of operating system for Gate that I have prepared while studying. So, in this, we were going to study about CPU scheduling and basically, in this, what we do is we schedule process on to the CPU, which is a job of short-term scheduler. Um, and one thing is one point to be noted is that completion and blocking can only done from running state. That I have already told, but that's the point you should remember. So there are a few terms that we should go over. First is schedule length. Schedule length is the completion time of last process minus arrival time of first process. So basically, schedule length is basically the length from which the CPU start processing till the end when CPU ends its process. Like the length of the total Gantt chart when the CPU is running. Throughput is defined as number of process divided by schedule length. As I have already told that throughput defined as number of job completed per unit time or the schedule length. Or schedule length is basically the time. Is basically the time or is in terms of time you can say. So when maximum CPU utilization is there, high throughput will be there. And yeah, there are other thing like waiting time, turnaround time, and run time. Waiting time is when process is ready to be scheduled, but CPU is not available. Turnaround time is defined as uh, when the process first arrived in the ready queue till the time it completes its execution. Runtime defined as the time during which the process run on CPU. Uh, the basic task of this CPU scheduling is to minimize wait time, turnaround time, uh, and runtime. Basically, runtime is dependent upon process, so we should not add here. This is the goal and the scheduling criteria for this. Response time of a process is the difference of the time at which process gets scheduled onto CPU for the first time to its arrival. Process time. Okay. The first waiting time in ready queue is known as the response time of a process. Okay. Yeah. So yeah, if IO bus time is zero, then process is always be CPU bound. Arrival time, yeah, as you can see here, the process times are here. So arrival time refers to when process moves from new to ready state. Waiting time means when process moves from ready state to again ready state, remains in ready state. Burst time means when it is scheduled on CPU. Turnaround time means completion time minus arrival time. Uh, and IO bus time and completion time. Completion time, the time after at which the process completes its execution. Response time of a request of a process. Response time of a request of a process is defined as the time at which the request is generated to the time at which it runs on CPU to generate the result and response. Yeah, it is same as that of response time of a process. Response time of a request of a process is the when is the time when request is generated to the time when the process runs on CPU. So there are multiple CPU scheduling algorithm, mainly first come first serve, shortest job first, shortest remaining time first, round robin, priority scheduling, and many more. So first come first serve. In first serve, the selection criteria is arrival time, which means those processes which arrive first will execute first. Mode of operation is non-preemptive, which means if a process is running on CPU, it will not get preempted until its execution is complete or it goes for IO operations. Conflict resolution. If If two process arrives at the same time, then process with lower process ID will get the preference. And the drawback is that it suffers from convoy effect. Convoy effect can be defined as when, if a large process with a big burst time uh, comes before okay, we can just rephrase it like, if there is a process with a very large burst time arrives first, and then the process with very little or small burst time arrive later, then uh, the that little process will starve due to the uh, first process. It is known as convoy effect, or like if a big truck is moving ahead of you and you cannot overtake, which will slow down the traffic, is known as convoy effect. Shortest job first. Selection criteria for shortest job first is burst time. Burst time, or the time required by a process to run on CPU to complete its execution. Its mode of operation is also non-preemptive, which means if a process is scheduled on CPU, it won't get preempted by any other process with lower burst time. And conflict resolution is again here with a lower PID. Select process with it selects process with lower burst time from ready queue and run till completion. It suffer from starvation. Similarly, if a like when only there is one process with a very large bus time is there, and as it is only one process, so it start getting executed on CPU or running on CPU. While running, many smaller jobs arrives or smaller process arrives in the ready queue, but it cannot preempt those which starve them. It is similar to that of the convoy effect that we have studied in first come first serve. The next scheduling algorithm is shortest remaining time first, SRTF. In this, the selection criteria is same as burst time, but mode of operation is preemptive, which means if a smaller process arrive, if a process with smaller burst time arrive, then it preempt the running process, currently running process. Conflict resolution when CPU is ideal, process with lower PID selected. So conflict resolution means if two process with uh, similar bus times arrive, smallest or the similar bus time arrive, then that process with lower PID will get the preference. Its drawback is preemption of running process is basically based on stricter shorter process. It's not a drawback, it's elaborating that preemption of a running process is strictly based on uh, shorter process. Now we will just performance comparison of SJF and SRTF. Both favors shorter processes. Both generate max throughput, minimize turnaround time and waiting time, and as they preempt larger process, so starvation to larger processes can be seen. Yeah, and there are practical limitation. SGF is not implementable because you cannot know the you cannot know the bus time of a process in advance, so you cannot implement these two algorithms for CPU scheduling, but it can be used as benchmark to assess the performance of other algorithms. Yeah, and it can all be implemented if you predict the bus time. With a predicted bus time or estimated bus time, these algorithm may be implemented. Next is longest remaining time first. Longest remaining time first, it's same. Selection criteria will be burst time. Mode of operation will be preemptive. And if a, la- it Longest remaining time first, as the name suggests, it favors the longest process. A process with a longer burst time. Tie breaking is the lower PID. Highest response ratio next. It's a type of a dynamic algorithm because its selection criteria based on response ratio, which is waiting time plus burst time divided by burst time. S means service time, which signifies burst time. Mode of operation is non-preemptive. It not only favors shorter process but limit waiting time of larger process. As the waiting time increases for as the waiting time increases for longer processes, it will increase their response ratio. Next is priority based selection criteria is priority in priority based. Each process assigned a priority and process with higher priority can preempt other process with lower priority running on CPU, and tie breaking is lower PID. In case of CPU is ideal and preemption is based on arrival availability of higher priority process. Round robin in round robin selection criteria is arrival time plus time quantum. In round robin, every process gets a certain time allocates a certain time to use a CPU, which is known as time quantum. Mode of operation is preemptive because if a process does not get completed within the certain time frame allocated, then it gets preempted and another process will run on CPU. Tie breaking again is lower process ID. Preemption of running process is based on time quantum or known as time slice. Uh, ReadyQ is FIFO based and improves responsiveness. Round robin improves responsiveness as a process gets preemptive after time quantum. This is a question based on FCFS. Scheduling overhead. Yep, we are not going any questions here. These topics. Yeah, now the next thing we're gonna be discussing here is like performance of round robin. As performance of round robin mainly depends upon the time quantum. So what happen if we select a time quantum too small? If we select the time quantum very small, uh, first of all, not very small, we will go for the small. If time quantum is very small, then context switching will be more, which means the scheduling overhead will be more. So CPUs spend more time doing context switching than executing, but it also make the system more interactive. But if the time quantum is large, then there will be less context switching and less interactiveness. And there are two extreme cases. If time quantum is very small, then CPU uses its means like context switching happening every other time. Uh, like if time quantum is very small, like one, so every one cycle the switching happens, which increases the scheduling overhead such that the efficiency turns out to be zero. And if time quantum is very large, if means like time quantum is like 10,000 units and no process exceeds ever like 5,000 process, then it just behaves like FCFS. And yeah, this point is important. Implementing preemptive scheduling needs hardware support. Basically, interrupts. Preemptive scheduling requires interrupts to do context switching. Basically, context switching uh, is uh, is a privileged instruction used by requires kernel support. We won't be doing this. Inter-process communication and process synchronization. Okay. Inter-process communication. If See, basically, process can only access its only its part of a memory. So kernel or OS prevents process to access any other part of a memory that is allocated to either to system or to any other process. So if two processes want to communicate, they uses inter-process communication. There is there is like three ways in which process can communicate. One is using pipes. Second is messaging passing system, and third is shared memory. Shared memory is basically when two process like P1 and P2 want to communicate, then they allocate a part of memory, both allocate a certain part of memory to be used as a shared memory. While message passing system, it is same as like passing a parameter to a function. Uh, to both IPC and pipes is like there is an actual connection between the two processes to be made in which communication is to be done. Uh, for inter-process communication, entity means function and done means parameter passing and global variable. Just I have said for message passing system, functions are used to pass information, and how we pass information in function using parameters. So why there is a need for synchronization? To avoid inconsistency, data loss, and deadlock. Type of synchronization. So there are two type of synchronization. When two processes are competing for the same resource, then it is known as competitive synchronization. And when two processes are cooperating, then it is known as cooperative synchronization. Cooperative means multiple processes get affected by each other, and in competitive, multiple processes compete for accessibility of shared resources. Okay, if we take an example of like a producer consumer problem, in which there is a producer and a consumer. Producer consumer problem is basically a cooperative problem. So a producer produces a food and consumer consumes the food, and both get affected by each other. If producer doesn't produce, then consumer can't consume, and if consumer stop consuming, then producer cannot produce more food, as the buffer will be full already. But competitive scheduling is like that dining philosophers, where each philosopher is competing for the folk to eat. Competitive synchronization leads to inconsistency and data loss, while cooperative may lead to deadlock. Examples for competitives are banking transaction, Amazon purchase, like how Amazon purchase, like there are only 10 items, means like 10 instance of a certain item is there, and 100 people want to buy this, so they will be competing for those 10 instance of a item. The reservation system, like there are only limited seats, and if more people want to buy seats, then it become a competitive scenario. Cooperative is like producer consumer problem. Application can have both competitive and cooperative problem. Application can have both competitive and competing problem. So this is a producer consumer problem. Here we define n equals to 100, which is the size of an array. Array is a buffer array in which producer cap the food. Initial count is 0. So here is the uh, producer function. We will focusing in this while loop. When a item is produced, first the item is produced while count equals to in count equals to n. Count equals to n is basically counting the number of item present in the buffer. If count equals to n, this means that the buffer is full. If buffer is full, then the producer needs to wait. If buffer in equals to 0 signifies like the index of the array or the buffer, where if the buffer is empty, where the item should be placed. This section of a code meant for like a circular queue type or a circular array type. And count plus plus is like is a part of the count plus plus, means it has now one more food. And now here count plus plus is like a competition, while the above code where the while loop is checking, it is like a cooperation. If we look for the consumer, if count equals to 0, which means that the buffer is empty and there is no food, then consumer can't consume, and it just loops in this statement. If there are item, then buffer, that item is taken from buffer and consumed, which is signifies by count minus minus. So both these, like producer and consumer, are competing for one variable, which is count. So both producer want to increase while consumer want to decrease. If there is like if we do not have a synchronization in these two tasks, then what happen is that the actual value of count may be false. Like example is like if producer initially produce two item and updates it, but consumer consume only one item, but before it updates in the buffer, producer produce another item. So according to producer, there now will be three item, but for consumer, but consumer think there will be only be two items because consumer takes one. This resulted in inconsistency for the count variable. Therefore, we need synchronization to avoid such instances. Necessary condition for synchronization problems. First is critical section. Critical section means where shared resources are accessed. Second is race condition. Race condition means situation when process access this critical section simultaneously, and final value is dependent on the order of their execution. Race condition is defined like if two processes are competing to change the value this of the shared resource. So the order of their execution defines the value of define the final value of the variable. So this is known as race condition. Preemption. Another necessary condition for synchronization is preemption. Basically, preemption refers like uh, it just preempt the another process before it's completing. Like we know what preemption is. Explaining this. Yeah, structure of synchronization mechanism. First, there is an entry section, and then there is critical section, then exit section, and then there is the remainder section, or also known as non-critical section. Both entry and exit section are used as a synchronization mechanism. Requirement for critical section problem to be satisfied. Like there are multiple answer to these critical section problem, but the requirements that need to be satisfied with multiple algorithms is that first is mutual exclusion, second is progress, third is bounded waiting. Mutual exclusion means only one process can execute critical section at a time. Progress means like if critical section is free and some process want to enter, then some process eventually enter. Process is like if process P1 want to enter the critical section and critical section is free, then P1 is allowed to enter critical section without any other like problem. Bounded waiting is like if P1 exits the critical section and P1 cannot re-enter the critical section again. So, like it's defined here as no process has to wait indefinitely to access its critical section. Like if there are three process, P1 is currently using the critical section. As soon as P1 exits the critical section, so P1 shall directly again not enter the critical section because already P2 and P3 are waiting. Progress means if like the critical section is free, or basically you can see that like currently P1 is executing the critical section, and after P1 exit the critical section, and now the critical section is free, but P1 again want to enter the critical section. So the P1 should be allowed to enter the critical section as there are no other process waiting, which is means progress. Mutual exclusion means no two process may be simultaneously access critical section at the same time. These three requirements are to be satisfied by synchronization mechanism. Synchronization problem, there are two type of synchronization problem. One is with busy waiting and another one is non-busy waiting. In non-busy waiting, basically the process which has to wait is gets blocked and need to be wake up when the required resources are available again. These problems are divided into three categories: software, hardware, and operating system. Software includes lock variable, strict alteration, Peterson solution, and Decker's algorithm, where hardware involves a test, set lock, swap, and disable interrupts. OS involves sleep, wake up, semaphores, and monitor. Semaphore, strict alteration, and Peterson solution are important with respect to gate. Assumption for solving critical section. These are certain assumption. First is finite amount of time to be spent in critical section. Second, a process can preempt from CPU while executing critical section in use. Means even if a process is executing critical section, it can get preempted. Process can get preempted while executing entry section. And fourth is process can leave critical section after executing exit section. So means these are the four assumption. First is finite amount of time to be spent in critical section. Process can get preempted either in entry section, exit section, or even in critical section. And process can leave can only leave critical section after executing exit section code. So first is variable. It's like there is a lock and there is only one key. So if lock is closed, then the process or the person can use that key to unlock. Uh, uh, okay. Here, okay. Repurpose this problem. Rephrase this like there is a room, uh, and if someone want to use this room, that person goes inside and lock the rooms from inside. So there can only be one person in this room. And if another person comes and sees the room locked, then it has to wait. And it can work with multiple processes, that there can be multiple persons want to access the same room. Okay. So here, if lock is open, which means gate is open, then if any person want to visit, then it closes the lock, executes the critical section, and lock can be and after his work is done in the room, it can exit the room by opening the lock and going outside, making the room available for another person or process to be used. Okay. But as we have making certain assumption for solving critical section is that process can get preempted. Uh, yeah, even while executing critical section, entry section, or exit section. So when the lock is open, after we execute, like between statement A and B, if process get preempted, then lock is still open. But for like if P1 is the person who first see the lock equals to open and goes inside, but before going in, it gets preempted, and P2 also sees the lock open, goes inside. So now there are two uh, person inside the room, uh, and both seeing the lock as open. Now, if assume that now P1 now preempts the P2 process, and now both the P1 and P2 now close the door, but there are now two person in the room, which means mutual exclusion is violated. If preemption happens after A with process P1, then the value of lock is not changed after A, because value of lock is changed only after executing B statement. So if P1 is the process and it get preempted after executing statement A, but then the value of lock remains same, means open. And another process P2 can enter critical section. And if P1 resumes, then P1 and P2 are together accessing the critical section, which violates mutual exclusion. Okay. This is the scenario which is seen like P1 comes executes A, then get preempted. P2 comes execute statement A as lock is open, then statement B, and then C. And after C is basically critical section, and point in critical section here. So now, after executing C, P2 gets preempted. Now P1 resumes. So as here you can see, both are accessing critical section at the same time. Progress is not violated as lock variable works independently. Bounded waiting is violated because some process can execute critical section multiple times while other process wait. Like if uh, there are three person waiting to access the room, and P1 continues to like entry exit, then it violates the bounded waiting. Second is strict alteration. It is also busy waiting, but it works only for two process solution. Uh, is basically a turn variable is used to assign whose turn it is to enter the room. If turn equals to 0, then process 0. If turn is equals to 0, then process 0 will enter the process. And if turn is not equals to 0, or basically if turn is 1, then process 1 enters the enters the critical section. So in this, mutual exclusion is not violated, as only there can only be one process entering. Either turn can be 0 or 1, it cannot be both at the same time. And progress is violated as If like P1 wants to use critical section, but the turn is of process P0, and P0 does not want to access the critical section, so P1 has to wait indefinitely or till the time that P not or P0 want to access the critical section. Bounded waiting is satisfied as same process cannot use critical section multiple times simultaneously access critical section. The same process cannot access critical sections simultaneously. Uh, okay, we will continue with Peterson solution uh, in the next part, and have a damn good day.